All right, so let's get started. Today we're going to be covering MRI basic principles. So as a reminder, I have the objectives posted on Canvas. So these are the things that we're going to be going over for the first two lectures. So I'm going to not read through them, but use this objectives as a good review guide. So if you have a chance, print it out and just kind of start filling it in, kind of like my X-ray physics class, where I used a lot of the objectives as test questions and things like that. So it's a great review if you want to use that. All right. So today we're going to start with that think, pair, share. And we discussed it last time, but I just want to review that document. So I asked you guys to compare MRI to other modalities like X-ray and CT. So I have the document that you guys created, and I just wanted to add a couple of things. So if you have this document, let's just kind of add to it. So when we're comparing MRI to CT and or X-ray, our advantages were better soft tissue visualization. We're not using ionizing radiation, so there's really no potential for biological harm. And we're on the electromagnetic spectrum, but where are we at? Higher or lower frequency? In terms of your frequency of that electromagnetic wave. What do you think? You think ionizing radiation has a higher frequency or radio waves? What do you think? Ionizing has a higher frequency. And then it higher frequency and a shorter wavelength for ionizing radiation. Remember that in that relationship? But radio waves have a lower frequency in the range of megahertz and a longer wavelength. So that's really what makes them less dangerous in terms of not being able to knock out electrons and cause ionizations, which can potentially alter your DNA, right? So those are the things that we've learned in X-ray, but let's now think about MRI and how it compares. Another advantage was your 3 orthogonal planes. And orthogonal, that just means 90 degrees from each other. So we're able to capture images in the sagittal, axial, and coronal planes. So as compared to X-ray, right, we have to kind of get one image and then reposition the patient into a lateral to kind of see a different perspective. CT, yeah, we're getting transverse slices that you can reformat into coronals and sagittals, but you're really getting one plane initially, your axials or transverse slices. But MRI is great because you can acquire a sagittal as your initial images or your coronals. So you can kind of just set it up to get any orthogonal plane that you desire. And you can actually even obtain oblique slices, which is great for, anatomy that is at an oblique orientation. MRI is now being able to be combined with other modalities, and we see this at Emory. We have an MRI IR suite at the main hospital here. We have a PET MRI scanner at Winship. And who knows what else we're going to start to combine in terms of the modalities. So right now we have nuclear medicine and IR already working with MRI guidance to better visualize those areas that they're delivering treatments to in real time. We also have a new technology in the portable MRI. It's a company called Hyperfine, where they're actually able to bring a small strength or low strength magnet up to the patient. So this is great for those ICU patients that are not able to transport COVID type patients. But the disadvantage, obviously, it is a low field strength, so you're not going to get the best image quality. But, if they're trying to see if they have a stroke, they do have sequences that they can visualize that. It gives you enough information to see what's going on. Another advantage is characterization of lesions or other various pathologies, and that really comes from better soft tissue visualization and increase what we call CNR, which is contrast to noise ratio. So you've probably talked about signal to noise ratio in the past, and like spatial resolution with your other modalities. But MRI is great in terms of contrast to noise ratio when we're able to tell one structure to another structure, those adjacent structures, and we're able to really tell the difference between those two structures. And ways that we can even improve upon that contrast to noise ratio is fat setting or saturating out the fat so it looks dark, so that if there is like a cyst or a tumor, you can see that as bright compared to that black fat. And then another fat suppression, a little different than fat saturation, is called a STIR, which is a short tau inversion recovery. And we'll talk about that when we get to pulse sequences, but that's an inversion recovery pulse where we're suppressing the signal from fat. Another advantage is we're using gadolinium contrast, gadolinium-based contrast, which by the literature has less reactions, usually less than 1%, than our iodine-based contrast. So our CT-based contrast, patients typically have a higher reaction rate than our gadolinium contrast patients. And then one I added here, we're able to do MRA imaging. And A is a little different than I, right? A stands for angiography. So we're not only able to see arteries, but we're able to see venous structures as well. So we can actually visualize like the circle of Willis, your carotid arteries, with a time of flight sequence. That's what we call it. And we don't even have to give contrast. So that's pretty cool where, you know, if you have a patient that is allergic to contrast, you can still see those vascular structures without injecting contrast, because we have specialized pulse sequences called time of flight imaging. But then we discussed some of the disadvantages. And one disadvantage was you're increasing your core body temperature of the patient, which corresponds with an increase in SAR, which stands for specific absorption rate. So as we deliver all these RF pulses to the patient, remember those radio frequency pulses to the patient, it's adding energy into their body. And so how they usually, you know, as those molecules start to vibrate, they get excited, and that usually heats the patient up. And it takes a little while for the patient to dissipate that heat. So we'll talk about some safety stuff in terms of SAR in our procedures class. The length of the scan. So we know that most pulse sequences are about, you know, range 3 to 5 minutes. But if you add up all the pulse sequences that we have, your scan time can be around 30 to 45 minutes. So if the patient happens to move, once again, we get decrease in our image quality. So motion is very detrimental to image quality. Another disadvantage is there's a lot of confusion between CT and MRI just because we have our circular donut-looking scanner, and they don't look much different from the outside, and an unknowing patient will easily confuse a CT and MRI and say, oh, I've had an MRI before, I've had a CT before, and they really haven't. They've had the other modality. So clarifying what's going to happen and what the expectations are crucial as an MRI technologist. Cost, we got some ranges, we got some different input from you guys last time about cost, but I usually say it's about around $4,000 if you had to pay out of pocket for an MRI, but it varies depending on if you're getting contrast, if the radiologist is reading this in a stat situation. So it's a very costly procedure, and you need to make sure your patients are going to, if they do have insurance, they're getting reimbursed. So making sure the order is correct and that they've contacted their insurance company to make sure that that particular scan, it falls under their coverage. Claustrophobia is a huge disadvantage for MRI because of that donut-shaped scanner that we deal with and having to push the patient into the middle of it. It's dark, it's confining, so claustrophobia is an issue. So the research says it's usually less than 5%, but I do not agree with that. Like I said, I think it's around 30%. You guys even gave me a higher number, like 50, 60%. So claustrophobia is an issue, and we'll talk about ways to handle those type of patients. Also, no call, no shows, and that might have to deal with like insurance reimbursement. But you know, some patients just get scared and they talk with their friends and they hear what's about to happen and they just don't show up, even though they've been put on the schedule. Number 6, not everyone can get an MRI. So we have a lot of MRI unsafe devices. So they have to go to another modality like ultrasound or CT to get their body looked at for whatever pathology or issues going on. Pregnant women might also be postponed or pushed towards another modality versus MRI. And then the last 2, loud gradient noises. We know an MRI machine is very loud, and what that noise is coming from, it's called the Lorentz force, but it's the gradient switching on and off very rapidly. So that loud banging is purposeful because it allows us to kind of spatially encode the data, but it is very loud and it's very noisy. And then cryogen safety, because we're dealing with superconducting magnets, which have that liquid helium or nitrogen surrounding those coils to reduce the resistance on those coils. But if for some reason those cryogens aren't able to vent out into the environment, they can get trapped in your room, and there's a lot of safety issues that come along with that. And we'll talk about that in the procedures class as well. So that is a good list of advantages and disadvantages of MRI versus other imaging modalities. Does anybody have any questions about that, or maybe even another one they thought about that they can add? Yeah?
I don't know if it's an advantage or a disadvantage, but that magnet is always on.
There you go. So safety issues. So we'll talk about, that's kind of the first thing I mentioned when we talk about MRI safety. The magnet is always on. So the potential that you have like something being brought into the room or somebody walking into the room that is not supposed to, that's why we have signs usually everywhere saying that the magnet is always on. So great, safety issues for sure. All right. So we'll pick up here. Okay, so today we're going to be going over properties of atoms. So a lot of this is going to be a review in terms of anatomical structure from our X-ray physics class, which I taught you guys, so hopefully you guys remember all that stuff. Interactions of those atoms with the magnetic field, and really dealing with the static magnetic field. So you'll see a little notation for static magnetic field, which is B sub 0. So if you have any questions about what that B sub 0, that's the static magnetic field, the stationary magnetic field. We're going to be talking about alignment of magnetic moments, or those vectors in our body. We're going to be talking about the equilibrium state, and then finally the net magnetic vector, which the acronym is just NMV. So you'll see that NMV a lot, but that stands for net magnetic vector. All right, so let's just do a little bit of review. So we covered anatomical structure back in X-ray physics, the first X-ray physics back in last spring, 2 springs ago. So it's been a while, so this will be a good review. So all things are made up of atoms, including us. And remember, atoms can be organized into molecules, which are basically 2 or more atoms arranged together. And molecules and compounds are a little bit different. A compound is 2 or more elements united in a fixed proportion. The most abundant atom in the body is hydrogen. So we obviously are comprised of mostly water, and you hear that saying all the time is your body is 70-80% water, and that's true. But you have other molecules in your body, and think of fats. You have an image over here of the organic structure of several fats, triglyceride, glycerol, and you can see that hydrogen is also attached in these structures. So you have hydrogen of abundance in the human body. So let's talk about that anatomical structure. So we have a central nucleus and orbiting electrons. And remember, the nucleus is very, very small. It says 1/millionth of a billionth of the total volume of the atom, yet it contains all the atom's mass. So do you remember which of the nucleons has the highest mass? The proton or the neutron? Do you remember? Which one has the highest atomic mass unit? Do you remember?
The neutron?
Neutron, because it's a combination of a proton and electron. Good. So the electron's very, very small in terms of its mass. The proton's almost the size in terms of mass of a neutron, but just slightly smaller just because the neutron is a combination of the proton and electron. And that's why it has no charge, because those charges cancel out. What's the charge of the proton?
Positive.
Good. So then that gives the nucleus an overall positive charge, right? Because we have a positive proton and then a no charge neutron in the nucleus. And then the electron that orbits our nucleus in shells. And what's the charge of the electron?
Negative.
Negative. Good. All right. So then atoms are characterized in two ways. You can describe it by its atomic number. And the atomic number is the number of protons within the nucleus. And usually the atomic number, or the Z number, gives the atom its chemical identity. And then you can also describe it as the mass number. Remember, the mass is the sum of the protons and neutrons. So it's usually balanced, so the mass number is even. However, some are slightly more or fewer neutrons than the protons. And in those cases, usually those are considered isotopes, where you have the same number of protons, but then a varying number of neutrons. Remember that? And so those isotopes are really what we're imaging in MRI. So they're very important. So we just talked about this with the protons are positively charged. Neutrons have no net or neutral charge. Electrons are negatively charged. And atoms are electrically stable if the number of electrons equals the number of protons. But that balance sometimes gets altered by applying external energy, like an X-ray, and knocking those electrons from its shell, those outer orbits of the atom. So when we knock an electron away, what is the overall charge now of the atom? Positive or negative? What do you think?
Positive.
Positive, right? Because we had one less electron, which was negative, so now the overall charge is positive. So this causes an electrical instability, and now these atoms are called ions. So remember, when you knock out an electron, you cause ionization. So there's a lot of motion going on in this atom. We have three types within the atom. So your electron is spinning on its own axis. So that electron is spinning on its own axis because it has a charge. The electrons also orbit the nucleus in specific energy levels. So remember that binding energy. So the binding energy is the highest in the K shell, which is closest to the nucleus, because that nucleus has that strong positive attraction. But then it gets less and less as you go further out. K, L, M, N, O, P. Remember all that stuff? And then finally, your nucleus itself spins about its own axis, depending on if it has a positive charge versus a neutral charge. So that can be variable. So that's why it's really important when we talk about those isotopes, where you have more positive than your neutral charge, or your neutrons, more protons than neutrons. So getting back to that nucleus and that motion in the nucleus. So if you have even mass number, that means you have, let's say, one proton and one neutron. So half the spin will be going in one direction from the proton, and then the other half will be going to the other with the neutron. And what happens is you get cancellation of the spin, and you overall get no net spin, because the neutron and the proton cancel, their spins cancel out. However, if you have an odd mass number, remember these isotopes, same number of protons, but different number of neutron. The neutrons are slightly more or less than the number of protons. So then the spin directions do not equal, and they don't cancel each other out. So let's think as basic as a hydrogen atom. So we have one proton and 0 neutrons. So then you got that proton and that positive charge spinning, let's say clockwise, but then the neutron doesn't, there's no neutron to cancel it out going counterclockwise. So therefore the nucleus has what we call net spin. And net spin can also be described as angular momentum. So these two words are interchangeable, and on the registry they like to kind of mix it up with how they present it. So just know that net spin is also described as angular momentum. And when you have net spin, these nuclei are known as MR active nuclei. MR active nuclei. Because you have a positive charge that creates spin. And what happens when you have a charged particle in motion? What does that create? You have a charged particle in motion. What does that create around it? A magnetic field. Good. So we're starting to see how we're creating little bar magnets within our body, which are important for when we put our patient into a very strong magnet. So we're creating little bar magnets. So here's that net spin. This is a good diagram of net spin where we have one proton and 0 neutrons within the nucleus, and you have spin. So the neutron's not going the other way and canceling it out. And this is kind of another diagram where you have, let's see, 1, 2, 3, 4 going to the right in terms of nucleons, and then 3 going to the left. So you have an overall spin going to the right called net spin. All right? So we have several MR active nuclei on the periodic table. Okay? And look at all of these atoms. What do you see that's similar about their atomic number or the isotopes of these atoms? What do you see? What did all these numbers have in relation?
Odd.
They're odd, right? Meaning you have a different number of protons versus neutrons. So that's important. You have an unbalanced nucleus, and it gives it net spin. But you can see here, carbon, nitrogen, oxygen, fluorine, sodium, and phosphorus. Why do you think those aren't imaged in MRI? Nice, nice. So right here, they're not as biologically abundant, right? You do have sodium, carbon, nitrogen, various places within the body, but it's just not as abundant as hydrogen. Remember, hydrogen, 78% is your body's comprised of water. But you also have other molecules that have hydrogen attached to it, like your fat. So what's cool about the future of MRI is as we get stronger and stronger magnets, we're actually now able to excite these isotopes and image specifically carbon or nitrogen or oxygen. Because we have the field strength now, like 7 Tesla, 13 Tesla, in like these lab settings, where our strength of the magnet kind of counteracts just the small abundance of that particular atom. So it creates a very small net magnetic vector of like nitrogen, but if you have a very strong magnet, that net magnetic vector gets larger and larger. So now we're actually able to kind of do experiments with exciting these other elements, which is pretty cool because it gives us other information about the patient's body. So that's kind of the future of MRI is you're able to image other MRI active nuclei. So these MR active nuclei are characterized by their tendency to align their axis of rotation to the applied magnetic field. So when we have isotopes, and we have a difference between the number of protons and neutrons, it creates little bar magnets, right? And little bar magnets inside a very strong magnet tend to align with that static magnetic field. And this is just kind of a breakdown, again, of the difference between the protons and neutrons, their nuclear spin, and these are called what we call half integral values, but you can see that hydrogen has a very strong vector quantity. And then just its natural abundance. So you can see that hydrogen really outweighs a lot of the other MR active nuclei. That's why we image hydrogen specifically. So the isotope of hydrogen that we focus on, yeah.
What is the half integral value?
Half integral, it's just talking about the strength of the magnetic moment that it's creating. So the strength of the little bar magnets that it's creating, basically. You can see that oxygen actually creates a stronger one, but once again, it doesn't have much natural abundance. All right, so this isotope of hydrogen that I keep talking about has a name, and that name is protium. So just make sure you know that isotope name, because that will definitely be a registry type question. Protium. Isotope of hydrogen. And once again, due to its solitary proton, it has a large magnetic moment, and that kind of corresponds with this integral value. So a large magnetic moment. All right. So when we have a moving charged particle, like I said, it creates a magnetic field around it. And remember, Faraday did a lot of research in terms of magnetic induction and moving charged particles and how it creates magnetic fields. So remember Michael Faraday, he had a large part in really helping MRI imaging evolve. But Faraday's law of electromagnetic induction states that a moving charge will create a magnetic field around it. Right? And remember the left thumb rule. You can also do it with the right thumb rule, where you have the charged particle as your thumb, and then your fingers were the magnetic field, well, parallel or perpendicular to that charged particle. Do you remember? Perpendicular, 90 degrees, yeah. So kind of the same concept here. So we're creating these little tiny bar magnets or small magnetic moments, which also can be described as a magnetic dipole. So you'll see a lot of these things used interchangeably. Magnetic moment, magnetic dipole, vector, quantity. A lot of times these are just interchangeable things. So try not to get confused by the terminology that they use in the book, because you really can just kind of use these interchangeably. They all kind of mean the same thing. But here is a great diagram just showing that a charged particle in motion will create a magnetic field perpendicular to that motion, and it creates like a little bar magnet with a north and a south pole, which is where you get the term dipole, two poles. So the magnet, or little magnetic moment of each hydrogen nucleus, has a north and south pole of equal strength. So that's where we get the term magnetic dipole. This north and south axis is represented by a magnetic moment, and you can describe that or just denote it as mu. So I'll just write it here just as a reminder of what mu looks like. Okay. And this magnetic moment has vector properties. Okay? So depending on how big that magnetic moment is and which direction it's pointing, you can have either the size of the vector and the direction denoted by an arrow. Okay? All right, so let's talk about vectors for a quick second here. So each magnetic moment has vector properties. And what those properties are size and direction. So make sure you know that for the registry. Size and direction. Every vector has a certain length, and it's pointing in a certain direction. Okay? So the top of the arrow is denoting the direction, and how long that vector is what we call the magnitude. You can also substitute maybe amplitude is another word you could use, but just the size of the magnetic moment. And these vectors, it's a little easier to kind of visualize when they're in these orthogonal planes, either going straight up or straight to the right at right angles to each other. But we know vectors can also be oblique. So when you have an oblique vector, you can actually break it down into smaller quantity vectors. Okay, so that's what this is showing here. But right here, I really want to just kind of show that when we talk about magnetic moment, your magnetic dipole, and vector, they all are really interchangeable. Okay? So when the book talks about it, this is one of those things that a lot of students get confused when they read this first chapter because they kind of use these terms and they interchange them at various parts within the first chapter, but they all mean the same thing. That hydrogen isotope, which is called what again? Protium, right? Has one proton and 0 neutrons within the nucleus. It creates net spin, and this is where you get that nuclear magnetic moment. This acts like a little bar magnet, can also be described as a dipole. And you can also describe it as this certain vector has a direction of that magnetic field and a magnitude. So how strong is this little Bauer magnet? And which way is the magnetic field pointing? Okay, so interchangeable. And then it's also important to remember that if this vector is sitting in an oblique fashion, you can divide it up into smaller vectors at those right angles. So this is a good diagram right here where it's got a long oblique vector. See how this oblique vector is very long, but then it can also be broken down into smaller vectors on those orthogonal planes. Okay, so the sum of these two vectors right here is equal to the oblique vector. And that's important when we start to talk about flip angles and tissue relaxation, which we'll cover in chapters to follow. Yeah?
So if you have, like, a certain number of vertical and a certain number of horizontal vectors, does it determine the angle of the oblique? Like, how much oblique is angle?
You could say that in terms of like how you divide up one particular vector, but we're going to be talking about here as we start to add up these vectors, we create what we call a net magnetic vector. And then we apply our RF pulse to put energy in that vector and to flip it down into our transverse plane. So that's going to kind of what we'll be talking about here with the flip angle. So I don't want to get it confused with just kind of adding up two vectors and creating a oblique vector. But yes, you're on to kind of the right concept. All right. So let's talk about these little bar magnets within our body. So this is what our hydrogen spins look like right now, where we don't have an external magnet. The only external magnetic field we have going on right now is just Earth's gravitational force. But that's not strong enough to align the vectors in our body, okay? Because it's about 0.6 Gauss, not very strong at all. But when we put them into a large scanner, which operate on what? What magnetic field strength? Not Gauss, but Tesla. And remember, 1 Tesla equals 10,000 Gauss, so very, very strong. So it will align these vectors. So, but just as a reminder, when we're outside that magnetic field, like right now, we're not even close to zone 4 of our MRI suite, these little hydrogen spins are pointing in every direction. So that's why it's important that we know they have a certain direction. Which way is this arrow pointing? Random. Right? They're spinning. They have a certain magnitude. And then they're pointing really in any direction. There's no rhyme or reason to these little spins inside of our body at this point. So once again, this is what it looks like with no external magnetic field, random. But when we're putting the patient and we're sliding them on the gantry into the middle of the magnet, that external magnetic field, which is in the range of Tesla, B sub 0, also called the ecstatic magnetic field, they will influence these spins in 2 ways. They will either align with the magnetic field, so here's B sub 0, and it's denoted by a large arrow. And imagine this arrow is pointing right through the middle of that scanner. And it's going from south to north. And then those flux lines are going from north to south. So these little spins are bar magnets within our body, hydrogen, either align with or they align against. There's not going to be any in between. There's nothing in terms of oblique, smaller vectors when we are influenced by the static magnetic field. That magnetic field takes over and it aligns them either with or against. So this alignment can be described in a couple of ways. You can describe it in the classical theory, and what the classical theory needs is just the direction of those little vectors. Just the direction. Which way is the arrow pointing? And they can either be parallel or anti-parallel. So which one do you think this one is in terms of B sub 0? So right over here, already improve upon this little drawing, put a little 0 here. Once again, this is the static magnetic field. How would you describe this little vector?
Parallel.
Parallel. Good. So this one's parallel. And then this one right here. Anti-parallel. Good. So either with or against. There can be no oblique vectors. All right. Got that down. You can also describe it as the quantum theory, which is really just the energy level of these vectors. And it can only be described as high or low energy. And these little bar magnets, just imagine, you have a very, very strong magnet that you just put your patient in. You have those little bar magnets inside their body. It takes more energy for that little bar magnet to oppose the static magnetic field than it is to just say, hey, why don't I just go ahead and align with it? So the ones that align with the static magnetic field, which we described as parallel, are considered low energy because it doesn't have enough energy to oppose it. And the ones that are anti-parallel, or what we call spin down, those are high energy because it takes more energy for that little hydrogen spin to oppose the static magnetic field, which is in the range of 10,000 gauss. So those are considered high energy. High energy spins. So, with that being said, which one over here is the low energy and which one's the high energy? If this is B sub 0 pointing up, which one's the low energy, which one's the high energy?
Top one's the high energy, the bottom one's the low energy.
Good. So high energy, top one, because it's opposing the static magnetic field, and then the low energy is the bottom one. Good. And don't be confused by these little circles right here and how it's kind of, I don't know, oblique, because we'll talk about that here in a second. That's called precession. So if you just want to simply draw it as just a straight up little arrow and a straight down little arrow, that's totally fine too with what we have covered thus far. All right, so this is a little diagram I created. So here is our patient. They're outside of the magnet. And see how their hydrogen spins are random. But once we put the patient inside the static magnetic field, B sub 0, they either align with or against. They either align with or against. So this is just another diagram showing that you have alignment with B sub 0. This is that blue vectors is B sub 0, or against the little red vectors. And you see that we have a larger amount of, what do you think, low or high energy spins?
Low.
Low. Okay, so we have an abundance of low energy spins. And that's what we'll talk about here with that equilibrium. But as we have an abundance of low energy spins, you get what we call the cancellation factor, where you cancel out 5 here and 5 here. So then that knocks it down to just 7 blue up. But those 7 little vectors add up to create the net magnetic vector. So we'll discuss it with a diagram a little bit later on in this lecture, but just that's kind of what that's representing. All these low energy spins, since there's an abundance of them compared to high energy spins, because remember, it's harder to oppose B sub 0, so there's not going to be as many. And through cancellation, we create what we call the net magnetic vector, which is so important in MRI because that's really all of our signal that we're getting from our patient. So here's just another diagram, kind of really hit home this alignment. This is outside B sub 0, they're random. Inside, they're aligned. And then one more. So if you like the bar magnet drawing, this one's for you. So you can see they're all random, north and south, pointing all different ways. But when the B sub 0 field is on, now they align. So this is a great summary slide. So highlight this slide, put a little star next to it, because this is a very common registry question where they'll ask, what's another name for anti-parallel? Or which one is not an example of spin up. So they have various ways they like to ask this. But let's talk about this alignment. So if they align with B sub 0, you can describe them as either parallel in terms of direction, which was our classical theory, or low energy, which was our quantum theory based on energy levels, and then just simply spin up. Spin up. As opposed to against B sub 0, you can describe them as either anti-parallel, high energy, or spin down. So make sure you know I guess you could call it the synonym of these various terms. So any questions about alignment?
Is there a particular theory associated with this?
No, I think it was just to simplify parallel and anti-parallel. But yes, good question. So I would maybe go that in the classical theory because it's really just describing the direction. But I think parallel and anti-parallel confused a lot of people, so they simplified it a little bit more by saying spin up and spin down. So this alignment is influenced by two things. One we've already talked about, the strength of that magnetic field, which is in the range of Tesla. And this is something that we can somewhat control. We can scan them on the 1.5 Tesla scanner versus the 3 Tesla scanner. But you're really confined to what you have in your department. And then the thermal energy of the nuclei. So the patient's temperature. So you're like, how does that really factor in? And it really doesn't really... we don't really have to consider this until we're actually doing like IR procedures. And it's pretty cool because we're heating up tissues and cooling down tissues based on various procedures that they're doing. And that patient temperature will influence relaxation rates and alignment of those spins. So they're able to actually get some information from those tissues based on the temperature of those tissues. So it's pretty cool. But that's really only something that we consider when we're really dealing with IR, MRI procedures. So this is kind of a summary slide. So those low energy nuclei do not have enough energy to oppose B sub 0. The high energy do have enough energy to oppose B sub 0. As B sub 0 increases, and what that's saying is you go from a 1.5 to a 3 Tesla, you'll have fewer nuclei that have enough energy to oppose. So now it even takes more energy to oppose a 3 Tesla versus a 1.5. So when that happens, you get less and less of the high energy and more of the low energy or spin-ups, and that creates a larger net magnetic vector overall. So that's ultimately why we get better signal with a 3 Tesla versus a 1.5, because our net magnetic vector is bigger to begin with. So when it comes to this thermal equilibrium, so at any moment in time, there are always going to be a greater proportion of spins with their magnetic moments aligned in the same direction, or you could say spin-ups or low energy, than against it. If we have more spin-ups than spin-downs, you're going to get an excess in that one direction, which produces that net magnetic vector. Excuse me.
Which is always, right? There's always going to be more.
There's always, yeah. There's always going to be more because it takes more energy to oppose than to simply just go with it. So there's always going to be an abundance of low energy. That's why we see here there's a deficit of the high energy by 4. And the cancellation factor is really just however many you have, and it's easier to kind of show it here on this next slide. We have 6 spin-ups, the low energy, and only 3 spin downs. So if you cancel out, okay, so I'm going to cancel out a spin down, a spin down, a spin down, but I also have to cancel a spin up to go with it. 3 of them. So you're always going to have an excess of spin ups. And this excess of spin ups, these are smaller little vectors, create the net magnetic vector. So this is the net magnetic vector. And let's just describe it as 3 smaller vectors. So you could also kind of write it like this, where it's just 3 smaller vectors. But when you add them up, it creates this net magnetic vector. And that is the most important thing for this particular unit. So that's the cancellation factor. You can read through that slide, but it's always better to kind of just draw it out and see how it actually does cancel them out. But here's another representation of it. The excess of the parallel spin-ups. And here I'm trying to use different ways you describe it. Parallel spin-ups, low energy, just so that you guys get used to it. The parallel spins, which are also low energy, the excess. You cancel out 3. I'd knock out 3. You have 4 left, and that creates your net magnetic vector. And back to this slide, in reality, it's not going to just be like 3 or 4 low energy spins that you add up to create. It's in the range of 4.5 million hydrogen spins that are going to be in excess for 1.5 Tesla, and then you almost double it for the 3 Tesla. Okay? So it's a lot of those hydrogen spins you're adding up to create that net magnetic vector. This is just showing you as you go from a 1.5 to a 3 Tesla, once again, it takes more energy to oppose, so you're going to get less and less of those spin downs at a 3 Tesla, so it creates a larger net magnetic vector. And then I always like to kind of show it in this fashion, because we keep seeing these vectors drawn straight up and down, right? But in reality, B sub 0 is actually running horizontal through the scanner. So we've seen B sub 0 on these previous slides going straight up and down, right? So that's why it sometimes gets confusing when we get into the room, because B sub 0 is actually running right through the middle of that magnet. So if you take a look here, this red vector is really that net magnetic vector that's aligning with B sub 0. Okay. So that's why they also call, this is the magnetization 0. That's parallel with B sub 0. And this is on your z-axis. But remember, we have our other orthogonal planes. This is the transverse plane right here where we have x and y, which correspond with your coronal and sagittal. And that's 90 degrees from this plane. So we'll get to that and how we excite this net magnetic vector to flip it into the transverse plane, because ultimately the xy plane is where we want that vector to get flipped down into, because that's where our receiver coil is on the patient. Okay? So ultimately, to get an MRI image, we have to do something to this vector. And we remember, we're applying those RF pulses. We flip it into the transverse plane, and it's rotating along this axis. And when we have a moving magnetic field around a coil, like on your receiving coil, it creates a current in that coil, and you collect that signal, and it ultimately creates, that's the most simplified version of how you create an MRI image. But those coils are right on this transverse plane. And it's a vector that's rotating around that transverse plane, creates signal in that coil, and you collect it. So in summary, The net magnetic moment of a patient is called the net magnetization vector, NMV. The static external magnetic field is denoted by B sub 0. The interaction of that net magnetic vector with B sub 0 is the basis of MRI. It's really where we get our signal coming from our patient. And as just a reminder, 1 Tesla equals 10,000 Gauss. So you have to be able to do that conversion for my test and the registry. So very, very strong magnets that we're working with. Any questions?